to see a few more kinds of equations today. Types of equations. This is 1,6 and 1,7. Our first type of equation is an equation in quadratic form. So this is not really anything new. It's like an equation in disguise, right? An equation disguised is something we don't know how to do, but we really know how to do it. So in our last class, we looked at how to solve polynomial equations and equations that contain radicals and rationals. Today, we continue our work with a special category of polynomial equations. Those are equations that are in quadratic form. Okay, so we know from our work in section 1.5 that a quadratic equation looks like this: ax squared plus bx plus c equals 0. So what do equations that are in quadratic form look like? So each of these equations that are in quadratic form, I've listed a quadratic equation next to it. What do they have in common? So we have x to the fourth minus 10x squared plus 9. And then I have x squared minus 10x plus 9. So what's the same about those two equations? Yeah. Yeah, so this is, the exponents are different, but the coefficients are all the same, right? 1, -10, 9. Same in both cases, right? And then in the next one, I have x plus 3 squared plus 7 times x plus 3 minus 18 equals 0. That is the same as x squared plus 7x minus 18 in the coefficients, right? This is 1 times something squared plus 7 times the same something minus 18. And 5x to the 2/3 plus 11x to the 1/3 plus 2 equals 0. Coefficients are the same, right? 5, 11, 2, 5, 11, 2. So when you have something that looks kind of quadratic, it looks like some stuff squared. We have stuff squared, a times some stuff squared, plus b times that same stuff, plus c equals 0. That's a generalized quadratic equation. Instead of just being x here, x squared plus bx plus c equals 0, now we can put any kind of stuff we want in there. And we'll be able to solve it by manipulating it into being a quadratic equation. So let's look at this first one, this x to the fourth minus 10x squared plus 9 equals 0. We'll solve that one. First, we have to decide what the stuff is, right? If we can make it look like this, some stuff squared plus b times some stuff plus c. So I have x to the fourth minus 10x squared plus 9. What is the stuff? What's being squared to get an x to the fourth? X squared, yeah. So I can rewrite x to the fourth as x squared squared. And I can rewrite, so then I have x squared here, and I have x squared here. So I have some stuff squared minus 10 times my same stuff plus 9 equals 0. So my hint here, or a useful technique, is called a U substitution strategy. To make this look simpler, we're going to let u be x squared just for a few minutes. Just to make this look nicer, I'm going to make a substitution. I'm going to let u equal x squared and make a substitution. So I start by writing x to the fourth is x squared squared, which then, if I use this substitution, replace my x squared with a u, and now it's just u squared. Okay, so over here, I'm going to have, instead of x squared squared, I have u squared. Instead of 10 times x squared, I have 10u. Does that make sense? Just replacing the x squareds with u's. And then, do you know how to solve this thing? You can factor it and solve it, yeah. So we factor the left-hand side, and I have u minus 9, u minus 1 equals 0. Set each factor to 0 and solve. We get u equals 9 and u equals 1. But we're not done. Why not? Why aren't those the answers? u is x squared, right? My original equation had x's in it. And when they ask you to solve for x, when they ask you to solve, they want, that is, tell me what x equals. What x's will make this true? So I have u's. So that's not really the answer. To get the x's, I go back up here, and I know that u equals x squared. So I replace u with an x squared. So I get x squared equals 9, and x squared equals 1. And I make another substitution. So I substitute u for x squared, and then I substitute x squared for u back at the end. So if x squared equals 9, what are my solutions here? Absolute value of x is 3, and absolute value of x is 1, which means that x equals plus or minus 3. Oops, what am I doing? Plus or minus 3, and plus or minus 1. You can go right to the plus or minus if you want, that's fine. All right, any questions on the basic premise here? Choose a u, substitute it in. Now it looks like an easier equation, solve it. Then you have to substitute the u back out. Put the x's back in. All right.
The purpose of it is not just look like it, but act like it.
Yes, yeah. Act like a quadratic, yeah. Turn it into something that is quadratic, and we know how to solve. We can factor or use a quadratic formula, solve it, and then go back to what made it complicated. Yeah.
Originally, it's not a quadratic equation.
Right, it's just a quadratic form, yeah. All right, so if I wanted to solve x plus 3 squared plus 7 times x plus 3 minus 18 equals 0, what would I let u equal? What's my stuff? X plus 3. Yeah, if I let u equal x plus 3, my new equation, instead of x plus 3 squared, is going to be u squared. Instead of 7 times x plus 3, it's 7 times u. Minus 18 equals 0. And now it's just a quadratic, right? Not too hard to solve. Does that factor? Yeah, 9 and 2. U plus 9, u minus 2. So u equals negative 9 or 2, right? But I'm not done. I have to go back and figure out what the x's are. I know what the u's are. I need to figure out what the x's are. And I know that u equals x plus 3. So I replace u with a negative 9. And I replace u with a 2. And I solve both of them. So I get x equals negative 12 or x equals negative 1. How you doing so far? You ready to try one? No answer? Well, you're going to try one. So I am helping you. I've given you hints along the way, so you can go through and solve this one by making a u substitution. Work on it in your groups, and I'll come around. All right, so we have 5x to the 2/3 plus 11x to the 1/3 plus 2 equals 0. So x to the 2/3 is x to the 1/3 squared, right? X to the 2/3 is the square of x to the 1/3. X to the 1/3 squared, right? Because when you raise a power to a power, you multiply the exponents. 1/3 times 2 is 2/3. So that's one of the key things to see in that problem, is that x to the 1/3 squared is x to the 2/3. So if I let u be my x to the 1/3, so I'm going to replace x to the 1/3 with u. That means that x to the 2/3, since we know that that's x to the 1/3 squared, ends up being u squared. So if I let u be x to the 1/3, this says 5u squared plus 11u plus 2 equals 0. That was one of the trickier ones of identifying the u. Okay, and then you can either use the quadratic formula or factor that guy. And it does factor, but if you use the quadratic formula, you get the same solutions. Either one is fine. Just to review the factoring, I want to set it up so that I have two binomials, two sets of parentheses, so that when I FOIL, I get the 5u squared plus 11u plus 2. So when I do the first term in each set of parentheses here, I need them to multiply together to make 5u squared. So I can only do 5u and u. Those are my only options because 5 is prime. The only things I can multiply together to make 5 are 5 and 1. Whole numbers anyway. All right, and then my lasts, right, what goes here and what goes here, those have to multiply together to make 2, the constant term. And there's only two choices for that, 2 and 1 or 1 and 2. So then we just check them both. If I throw a 2 here and a 1 here, then when I do the outer and the inner, I get 10u plus 1u, which gives me the 11u that I need. So I have 5u plus 1 times u plus 2. Then you set each of those factors to 0. Sorry, so I'm just going to put these in the boxes they belong in here. Set each factor equal to 0, and we get u is -1/5, and u equals -2. Set each factor equal to 0 separately, and solve. But we're not done, because we're trying to solve for x, right? We still need x. So I go back to my equation that relates u and x. U equals x to the 1/3. And I replace the u with each of the values that I got before. So I have -1/5 equals x to the 1/3, and -2 equals x to the 1/3. How do I solve these guys? Raise them to what? The third power, yeah. So x to the 1/3, if I raise it to the third power, 1/3 times 3 gives me 1, right? So, because when I raise a power to a power, you multiply the exponents. So I think, okay, what should I raise this to so that when I multiply those two numbers, I get 1? And so the third power works. Or you can think of x to the 1/3 as the cube root of x, and then to undo cube root, you cube. So x to the 1/3 cubed is x to the first, which is the same thing as x. And -1/5 cubed just means -1/5 times -1/5 times -1/5. So the answer is going to be negative because I've got 3 negatives. And 1/5 times 1/5 times 1/5 is 1 over 125. Yes. Yeah, what is it? -0.08? Something like that? 0.008, yeah. Yep, that's fine. And then we're going to use the same method over here, cube both sides. So x to the 1/3 cubed is just x. -2 cubed is -8. Finally, we should list the elements in the solution set if I want to use this notation. -1 over 125 and -8. On a test or a quiz, if you don't put your solutions in set notation, that's okay. I just want to get you in the habit of it because my math lab sometimes asks you to do it that way. They already put the brackets? Oh, okay, good. All right, so now we're gonna, that takes care of solving generalized quadratics, right? When you have some stuff squared plus something times the same stuff plus a constant equals 0. Generalized quadratic. All right, so now we're going to do equations involving an absolute value. We've already solved really simple ones of these. If the absolute value of x is 3, what could x be? 3 or negative 3, right? Because the absolute value of 3 is 3, and the absolute value of negative 3 is also 3. So the absolute value of x is 3 means that x could be plus or minus 3. But I just want to look at this graphically just to wrap our minds around it a little bit more. Okay, so go to y equals. If there's anything there, clear it. Okay, so when you solve something graphically, you put the left side of the equation in y1 and the right side in y2. This is one of the ways to solve graphically. So in y1, I'm going to put the absolute value of x. So where you find absolute value is in the math menu. Cursor over to number. So you use the right arrow to get to the number menu. The first option is ABS for absolute value. And I just want the absolute value of x, so I type in an x there. Some of the newer TIs actually have the notation. When you choose absolute value, you'll get absolute value bars. Just put an x inside. Math button. Then go to the number menu. You have to use the right arrow to get to the number menu. Option 1 is absolute value. All right, so you have absolute value of x in y1. In y2, I'm going to put the right-hand side of the equation, right? The 3. So y1 is absolute value of x, y2 is 3. And I want to see where these two graphs cross. So I'm just going to do zoom 6, the standard viewing window, absolute value of x, and 3. And you see they cross in two places, right? One's negative x equals negative 3, and the other is x equals 3. So I'm just going to take a quick picture of this. Okay, so the x coordinates of the intersection points are x equals negative 3 and x equals 3. Negative 3 and 3. So those are our two solutions. We can generalize this observation for all absolute value equations. Okay, if you have the absolute value of u, and again, u could be any stuff. It doesn't have to be just a plain old variable. The absolute value of some stuff equals a number, then either that stuff equals c or it equals negative c. So let's say I want to solve the absolute value of 2x plus 1 equals 11. To rewrite the equation without absolute value bars, I have to translate this into two different equations. Whatever I'm taking the absolute value of, whatever is inside those absolute value bars, if the absolute value of it is 11, then that stuff either equals 11 or it could equal negative 11. Right? If you take the absolute value of some stuff and it's 11, either that stuff is positive 11 or it's negative 11. Does that make sense? All right, so now I have two different equations to solve, and here I get x equals 5, and here I get x equals negative 6. Okay, I already did that. So let's check both of our equations. When I plug 5 in, I want the absolute value of 2 times 5 plus 1. Does that equal 11? Well, 2 times 5 is 10, plus 1 is 11. The absolute value of 11 is 11. Yeah, so that checks out. And then I'm going to check the negative 6. Do that in another color. So I have 2 times negative 6 plus 1 in absolute value. Does that equal 11? Well, 2 times negative 6 is negative 12. What's negative 12 plus 1? Negative 11. Is the absolute value of negative 11 equal to 11? Yes, then this is true also. Uh-huh. Yeah. What do you mean? Yes, we want to rewrite it without absolute values. No. Okay, this is a great question. So we just learned how to solve an equation that looks like the absolute value of some stuff equals a number, right? So this is like, I'm going to dump the bucket of water on the floor, right? I look at this one and I go, okay, I know how to solve the absolute value of some stuff equals a number, so I'm going to make this look like that before I try anything. So I'm going to subtract 4 from both sides, right? And I have 3 times the absolute value of 2x minus 1 equals 21. Divide both sides by 3. And I get the absolute value of 2x minus 1 equals 7. And yeah, so you want to isolate that whole absolute value first, right? Isolate. Treat it like a variable, solve for it. And now it looks like it looks almost exactly like the problem we just solved. Now I know how to solve this kind of thing. Once I have the absolute value of some stuff equals a number, I can just say, okay, well, either my stuff is 7 or my stuff is negative 7. If I take the absolute value of it and I get 7, it is either 7 or negative 7. So then I solve both of these and I get 2x equals 8 and x equals 4. Or 2x equals negative 6, so x is negative 3. That makes sense? Dump the water on the floor. Yes. Nope. Because I do not set it equal to positive 25 and negative 25. You only do the positive and negative thing at the one step where you're getting rid of the absolute values. Once you have the absolute value isolated, then we set 7 and negative 7. Make sense? Okay. All right, so I would like you to discuss with someone next to you why the absolute value of x plus 4 equals 2 has no solutions. All right, let's take a quick look here. Absolute value of x plus 4 equals 2. If I isolate the absolute value, before I start thinking about, what x is, subtract 4 from both sides. So I get the absolute value of x equals negative 2. Is there an x value that I can plug in there and make that equation true? No, why not? Because absolute value is always positive. There's no way I can take the absolute value of something and get a negative. All right, so this is never true. Because the absolute value of anything is always positive. Let's take a quick look at the graph. If I wanted to solve this graphically, I would do y1 is absolute value of x plus 4, and y2 is 2, right? And then I would see where they cross. Let's see what happens. You think they will not cross. That makes sense, right? So y equals I'm going to do the absolute value of x plus 4. So I do math, number, absolute value of x plus 4. Putting the plus 4 outside the parentheses because it's not inside the absolute values. And 2. And then I'm just going to do zoom 6. And they never cross, right? So they have no points in common. They never intersect. So those two are never equal. Okay, next thing, solving linear inequalities. So here's an inequality, x is less than or equal to 7. I want to graph the solution set. How do I do it? Like that. X is less than or equal to 7. So we can graph the solution set. Or we could use set builder notation, which we learned earlier in the semester, which was the curly bracket x, set of all x's such that x is less than or equal to 7. Okay. But we have another, possibly more convenient way to represent solution sets called interval notation. Okay. So the way that I would represent this particular set is I would put negative infinity, comma 7. So when you have an interval, you put the left endpoint and the right end, comma the right endpoint. So you always put the smaller number on the left, bigger number on the right. If you include the endpoint, you put a square bracket, and if you don't include it, you put a round bracket. So I have a square bracket on the 7 because the 7 is included in the set, right? I put it because it's or equal to. Why do you think I put a round bracket on the negative infinity? Yeah, negative infinity isn't a number. It's not an endpoint of an interval. It just means keep going forever, right? So you can't ever get to infinity, so we can't include it in the set. Davis, you had your hand up. Do you have a question? Oh, okay. Sorry. All right. So the parentheses negative infinity to 7 represents the same solution set as this set builder, the set of all x such that x is less than or equal to 7. So closed, open, infinite intervals, these are all possibilities. If I have 2 comma 3 with square brackets, that means all the numbers from 2 to 3, including the 2 and the 3. So if I were to graph it, it would be closed dots on 2 and 3, and the shaded in between.
So the square bracket.
Yes, or equal to. Yep. So it means the same thing as the set of all x, such that 2 is less than or equal to x is less than or equal to 3. And then here's another example with round brackets this time, parentheses, indicates that the endpoints are not included in the interval and are not solutions. So I here -1 to 5. Again, smallest number on the left always, biggest number on the right always. So we have -1 to 5, but we're not including the endpoint, so you put open circles on them. And then here we have an example that's half open, half closed. -4 to 1. This time we're including the -4. Sorry, not including the -4, and are including the 1. Because there's a round bracket on the -4 and a square bracket on the 1. Infinite intervals are places when we have negative infinity on the left or positive infinity on the right. And we always use a parentheses because infinity is not an actual number. All right, so now that we have this interval notation, we can use it in a really handy way when we're solving linear inequalities. So linear inequalities are solved just like linear equations. You do the exact same steps that you would do if this was an equal sign as opposed to a greater than or equal to sign, except for one rule change. Anybody know what the rule change is? It has to do with negatives. Flip the inequality when when you divide by a negative or when you multiply by a negative. If you multiply or divide by a negative, the alligator turns around. Okay. So, yeah, my third grade teacher, I think, used when she taught about inequalities, she used this alligator analogy. The alligator always eats the bigger number. So this says 3x plus 3 is bigger than or equal to 0 because the alligator's eating it. And this one says negative 4x is smaller than 8 because the alligator's eating the 8. And when you multiply or divide by a negative, the alligator turns around. Okay. So we're just going to solve both of these. 3x plus 3 is greater than or equal to 0, which means 3x is greater than or equal to negative 3. Divide both sides by 3. And the 3's cancel. I get x, and I get negative 1. Should I turn the alligator around? Why not? Right, I'm dividing by positive 3, so I do not have to turn around the alligator. So I get x is greater than or equal to negative 1. If I'm going to put it in set builder notation, I would put the set of all x's such that x is bigger than or equal to 1. Negative 1, thank you. Interval notation, maybe it would help if I graph it first, right? X is bigger than or equal to negative 1. So I'm including the negative 1, and all my numbers are bigger than it. So I go to the right. How would I write that in interval notation? Bracket, negative 1. Perfect. Negative 1 comma infinity. Include the negative 1 with a square bracket. Don't include the infinity because you never include infinity. Okay. On the interval notation, I'm just putting the answer, right, in a different format. I'm starting at negative 1 and heading towards infinity. So we put negative 1 comma infinity, and then I put a square bracket on the negative 1 because I include it, and a round bracket on the infinity because infinity is not a number. It can't be in the set. You'd put the negative infinity on the left because you always put the smallest number on the left. Yeah. All right, so negative 4x is less than 8. If I want to solve this, I'm going to divide both sides by negative 4. And I'm going to have my negative 4's cancel, and I have x on the left, and on the right I have negative 2. Do I turn the alligator around? Yes, I divided by a negative, so I turn the alligator around. X is greater than negative 2. So strictly greater than, so I'm going to use an open dot. And bigger than means to the right of. So I shade over here. So my set builder notation is just adding some fanciness to what I have right here, right? I have curly brackets, the set of all x such that x is bigger than negative 2. And interval notation, though, I would put negative 2 comma infinity, right? Because I start at negative 2, I head towards infinity. Am I going to include the negative 2? No, so I use a round bracket. And I use a round bracket on infinity all the time. So the rule change is the alligator turns around if you multiply or divide by a negative. Oh my goodness. Yeah, I need new markers. Negative, you can kind of see what that says. Okay. All right, so if we have an inequality that has some fractions in it, if I want to solve x minus 4 over 2 greater than or equal to x minus 2 over 3 plus 5, 6, or 3 times x minus 4 greater than or equal to 2 times x minus 2 plus 5. Which one of those would you rather work on? The one on the right, yeah. Well, you know what's really handy is that those two inequalities are the same. They have the same solutions. They're equivalent. And the way you can turn this one into this one is by multiplying by the LCM. So let's apply this. I have x minus 4 over 2 is greater than or equal to x minus 2 over 3 plus 5 over 6. 6 is the LCM. Good. So I'm going to multiply both sides of my equation by 6. Every term on both sides. And some people, it's really helpful to write 6 over 1, right? Because you remember that the 6 is in the numerator. All right, so if I have 6 times x minus 4 over 2, the 6 over the 2 can reduce to a 3, right? You say, okay, well, 2 goes into 2 once, and 2 goes into 6 3 times. So this becomes 3 times x minus 4, greater than or equal to. All right, so then I have to distribute this 6 to both terms in parentheses. And when I multiply 6 times x minus 2 over 3, the 6 over the 3 reduces to 2. So this becomes 2 times x minus 2. And then here I'm going to multiply 5 over 6 times 6 over 1, and that reduces to what? 5. 6's cancel. You just get the 5. So now we just solve this like any other inequality, and you can do it on your own. All right, so the last kind of inequality we have is a compound inequality. Very good. So in this case, the following two inequalities could be combined into a single statement. So if I say negative 6 is less than x minus 4, and x minus 4 is less than or equal to 1, how could I combine them into a single statement, just to be more efficient? Mm-hmm. Or, go ahead. Oh, okay. I'm not going to solve it just yet. Okay. But so here you wrote, this is true. 1 is bigger than x minus 4, which is bigger than negative 6. But just because of the way we picture a number line, left to right, smallest to biggest, I tend to write things left to right, smallest to biggest when I write compound inequalities. So I would do negative 6 is less than x minus 4 is less than or equal to 1. It's kind of like a run-on sentence, right? So this is because when you first learn about equations and inequalities, you think of the equal sign or the greater than sign as the verb. So this is kind of like negative 6 is less than x minus 4 is less than 1. It's like a compound sentence. And then if I want to solve it, I have x minus 4 sandwiched between two things. To get the x by itself, I'm just going to add 4 to all three sides. Right? So I have negative 6, less than x minus 4, less than or equal to 1. Add 4 to all three pieces to maintain the relationships. And negative 6 plus 4 is negative 2, is less than x, is less than or equal to 5. And then how would I write that in interval notation? Perfect. all the numbers between -2 and 5, not including the -2 because it's not or equal to, but including the 5 because of the or equal to sign. How will we use our graphing calculators to solve that inequality? Any ideas? Well, what do we usually do when we solve equations graphically? Yeah, so we usually have two sides of an equation. We put them in as y1 and y2. But when you have a compound inequality, we have sort of three sides, right? The left, the middle, and the right. So I'm going to put in all three. So the left was -6, the middle was x minus 4, and the right was 1. And then let's see what kind of a picture we get when we do that. Okay, -6, x minus 4, and 1. And I'm going to look at just a standard window, zoom 6. Okay, so I'm looking for places where this line, x minus 4, is between -6 and 1, right? So I'm looking for places where x minus 4 is bigger than -6, but less than -1. So that would be like in between -6 and 1. So yeah, it's all the numbers where the line is sandwiched between the two horizontal lines. Yeah. Yeah, where it intersects the top line because of the or equal to part. Yeah. So this is going to be right here, which is -2, where they cross. -2 to 5, including the 5. Those are the x values where the x minus 4 line is between the two horizontal lines. All right, so there's only 4 minutes left. So we have this group exercise for selecting a better deal. You could start on that, or I'm going to hand out the take-home quiz, and you could take a look at that if you want.